Yes, so today, indeed, it will be about ongoing efforts. We're not quite there yet with the quantum memory, but hopefully in 1 or 2 years' time, that's our time scale. We'll be showing how nuclear spin can be used as a resource to store the quantum state of an electron. So the way I motivate this work really usually is by looking at you know, what's been done with quantum dot thus far. And I think one of the most advanced experiments that one can do with any system and any spin photon interface is actually to create entanglement at a distance. And if you look at quantum dots, they're actually the fastest system that you can entangle remotely. And that's all thanks to their great optical quality. The fact that, you know, you emit a photon with almost 100% quantum efficiency, a coherent photon, if you remove the 10% of phonon sideband. And these photons are really indistinguishable and can be used towards creating entanglements. So you typically reach entanglement rates in these systems which are on the order of kilohertz, and this can be further improved by integrating the quantum dot in waveguides or in micropillars or open microcavities. And this is really well beyond any other physical system. So the next step is, well, to go beyond 2 nodes and actually extend entanglement to 3, 4 remote nodes. And for that, you need to have an ancilla memory. You need to have a qubit on which you can store a given entanglement link that you have created. And to do that, what we are investigating right now is the possibility to do this using nuclear spins in a quantum dot. So for the sake of this talk, the quantum dot will be a simple man-made artificial ion. It's an ion because we've loaded an electron, a charge in it, which has 2 spin states up and down. And these ground states of the quantum dot, of course, coupled to optically excited states that you can address resonantly with lasers. And this electron spin, well, is a well-controlled, simple quantum system. We know how to initialize and read out the qubit with resonance fluorescence. And we can, in fact, create or measure any quantum superposition by shining an optical field, via a Raman process. We can essentially mimic the spin control that one has with standard radio frequencies, standard electron spin resonance techniques. And of course, this electron is located in a quantum dot, and within the quantum dot at each lattice site, there are nuclear spins. And so this electron strongly couples to an ensemble of 10 to the 4, 10 to the 5 nuclei. And this many-body ensemble of nuclear spin, you know, it was long predicted that it was actually fairly isolated from the rest of the semiconductor matrix. The main thing it would couple to was the electron spin, such that you could actually use this system to study emergent phenomena, exotic phase transitions, and also use these nuclear spin as a robust collective memory to store the electron spin state. And so much of the talk today will be dealing with how we can use this electron spin to control and probe this more complex quantum system of nuclear spins. And so all this is based on a spin control technique that we have developed in the last 2 years ago, roughly, which is really identical to electron spin resonance. So as you see here, what I'm showing is nice spin-Rabi oscillations as a function of drive time. And by controlling the laser power, and by we can increase the Rabi frequency, so the speed of the rotations. And we can also, importantly, modulate the phase of our laser field to actually create a gate around any arbitrary axis. So now we can do multi-axis spin control, which is a very important thing to have in your toolbox if you're thinking of coupling control linked to nuclear spins. And all the nuts and bolts of this technique are summarized in this NPJQI paper. So now, what is there to know about the fact that we're dealing with an ensemble of nuclear spins rather than a single nucleus? Well, to quote a famous physicist, it's because more is different. And one way to think about this is to take a simple quantum system, you know, a two-level atom. You all know how it behaves. You can take it to the excited state. It will decay one photon with an exponentially decaying probability, which characterizes the lifetime of your emitter. And already, when you take two of these quantum systems, things can behave in a strange way. So let's take two of these quantum systems with one atom in the excited state and one in the ground state. And let's suppose that they are at different locations, far enough such that they don't interact directly, but they are close enough compared to lambda, which is the wavelength of your photon. So this example is actually taken from Dicke's seminal 1954 paper. And the question is, what happens here? Well, what happens is fairly counterintuitive. The emission of this two-body system is actually that you will emit, on average, half a photon, and the lifetime here will be faster than the lifetime of your single atom system. And the reason for that is because, in fact, the vacuum field interacts with both systems in an identical way, such that the eigenstates of the system with respect to photon emission is actually either an antisymmetric state, a dark state. So dark nuclear states are also a thing, as for those who've read a bit of the literature, and a super radiant state, which is a symmetric combination and which has an enhanced radiative decay compared to your single atom. And so these effects have been, you know, sought after fairly early on. The first experimental verification of collective effects came from the Serjarov group in 1983, where they coupled atoms to the single mode of an optical cavity, a single optical mode. And since then, you know, collective phenomena such as super radiance, etc., have been observed with Rydberg atoms, trapped ions, superconducting qubits, and they have long been, you know, proposed as early as 2002, I think, roughly. They have been proposed to occur as well in a quantum dot. And the reason being that the electron spin is analogous to the single optical mode of your cavity, which couples homogeneously, fairly homogeneously, to the nuclear spins of the quantum dot. And so the question now is how to control these nuclear states via the electron spin. So the way we're going to do this is, well, before I explain how to, sorry, I'm first going to explain the sort of eigenstates of our system. So let's take the electron spin and the nuclear spin state in an external magnetic field. Our electron spin will be split by the Zeeman energy. So this is what I in this diagram happens if you go from bottom up. And from left to right here, I'm changing the nuclear state by a single spin unit. And so the energy scale associated to these spin flips is the nuclear Zeeman energy. So we have two energy scales, the electron and the nuclear Zeeman energy. And we have, of course, a third energy scale, which is the hyperfine interaction, which is this constant AZ, and gives rise to the so-called Overhauser effect, which is a shift of the electron spin resonance depending on the value Iz of the nuclear spin polarization. And our goal is to fully control this quantum system. So somehow we want to be able to controllably go from one electron nuclear state to another one with a different nuclear spin state. And our approach is to do this by using a non-collinear hyperfine interaction. Non-collinear because in your Hamiltonian term, you have an IX operator for the nuclear spin and an SZ operator for the electron spin. So in other words, you are able to flip a nuclei without flipping the electron. But this process, if you just have this Hamiltonian alone, is frozen, because to flip a nuclear spin, you need to provide the nuclear Zeeman energy, so it's energetically forbidden. But now, if you start to modulate SZ, and this is just a semi-classical picture here, where I have replaced SZ by an oscillating field at the nuclear Zeeman energy, then this non-collinear term can give rise to nuclear spin flips. And if you do actually a full quantum treatment, you end up with exactly a spin exchange Hamiltonian between the electron and the nuclear spin, where your S- operators here are operators which operate in the electron dress state basis. And you flip nuclear spin in the lab frame. So, and then to conclude about these sort of nuclear spin flips, of course, because we're dealing with an ensemble, we actually have a spin flip which is intrinsically distributed across all nuclear spins, and we have a collective enhancement when we're triggering these and imprinting those spin excitation. We have a collective enhancement of √10 times the single nuclear spin hyperfine constant, non-collinear hyperfine coupling constant. So can we control quantum dot nuclear states via the electron? So the first thing which is important, but that I will not detail right here, right now, is that actually if you want to launch these nuclear spin excitation, you need to prepare the nuclear state, because naturally your nuclear state looks like this red curve is something which is incredibly broad. The uncertainty on the nuclear spin polarization Iz is hundreds of megahertz, which is much larger than the 20 megahertz of nuclear Zeeman energy. So you're not able to resolve the sideband process. So to be able to resolve them, you're going to prepare via a technique which is very similar to Raman cooling in atomic system. You're going to prepare the state in a non-thermal state where you have vastly reduced the Iz, the uncertainty on Iz, down to a few megahertz, which is much smaller than the nuclear Zeeman energy. And so once you have done this preparation, now we're going to try to drive these sideband processes. So here what I'm showing is going back to this energy level. Here I have the central electron spin resonance, but we are going to drive these resonances detuned by changing delta, the detuning of our drive, and we're going to be looking for these sideband transition. So we did this experiment. This is a full 2D map showing you the electron spin population in height. as a function of the detuning of your drive and the drive time of your ESR. So, and down here, what I'm showing is a line cut of this 2D map at short time. So at short time, as a function of detuning, this data yields the blue curve, which is a single peak corresponding to the central ESR transition. And now, if you do the same light cut, but at longer delays, you will actually observe that you start to transfer electronic population via these weaker sideband processes. And so the light cut here is, this blue curve, which yields a well-resolved structure corresponding to electron nuclear transitions taking place at once or twice the nuclear Zeeman energy. And so why do we have not only one unit of spin flip, but also 2 units of spin flip possible in these sideband processes? The reason for that is that physically, these electron nuclear spin flips and the non-collinear interaction that we have actually arises from strain and from the quadrupolar interaction on our high species nuclei. So if you look at this non-collinear hyperfine interaction, it actually looks very similar to a quadrupolar Hamiltonian with terms which are quadratic in the I operators. And you have these terms which are linear in IX that will give rise to delta M equals 1 nuclear transition, if you look at the single nucleus picture. And these terms which are quadratic in IX and IY, which gives rise to delta M equals 2 nuclear spin transitions. And, again, physically, this Hamiltonian arises because you have a real magnetic field and an effective magnetic field, the quadrupolar field, which tend to blur the quantization axis of our nuclear spin here, and it makes the different spin states. And this quadrupolar interaction, in fine, perturbs also the axis of the electron nuclear hyperfine interaction. And you can see that if you look at this non-collinear coupling constant, it's actually the collinear hyperfine coupling constant times BQ over BZ times, theta, a geometric factor. So it's really the collinear times the perturbation, how BQ, the quadrupolar field, perturbs the main quantization axis. Right, so now we have this. The question is, can we actually reach a regime in which these electron nuclear processes can be driven coherently? And we found, and we demonstrate in our science paper, that this is the case. You can actually have a Goldilocks region between 9 and 16 megahertz for the electron Rabi drive, where you're sufficiently fast to beat decoherence in your system, nuclear inhomogeneities and electronic decoherence, and you're sufficiently slow to talk to a single nuclear species. And so in this regime, you can see actually damped, but yet you can clearly resolve Rabi oscillations between these two states as you coherently drive them. Right, so now I will tell you about what we have done during lockdown, or should I say before lockdown. The next question is, until now we've read and we've inferred nuclear spin flips just from looking at the population of the electronic state. But the question I want to answer now is, can we directly detect a nuclear magnon? So what do I mean by that? If we write a magnon in the nuclear ensemble, we have seen that via the collinear hyperfine interaction, we should, in principle, shift the energy of our electron spin states by the hyperfine constant AZ, which is on the order of 500 kilohertz. So the question is, having driven a magnon, can we actually detect that the transition energy of the electron has shifted by the nuclear hyperfine? And to do this, we're obviously going to use a Ramsey sequence to measure very precisely the electron spin splitting, sorry. And we're going to do a Ramsey sequence with a slight twist. It's called the side-of-French measurement, because actually our two Ramsey pulses, which are two subsequent pi-half pulses, are carried along orthogonal axis. So the first axis is along x, the second one is along -y. And the advantage of this sequence is that at the end of your readout, the spin population difference of the electron readout will be actually evolving linear in delta omega. I'm saying linearly because, you know, obviously delta omega is very small. So this overall quantity in the sign is a small quantity, and with this side-of-French measurement, just like an optical interferometer at the side of the fringe, you are maximally sensitive to small path variations in your interferometer. And this is exactly the same with the electron spin, maximally sensitive to changes in the Overhauser field. Furthermore, you can't increase tau indefinitely. You obviously are limited by T2 star effect. This is really a Gaussian decay that on your signal. And so to maximize your sensitivity, you want to place yourself at a delay, which is T2 star over root. And T2 star in our case is roughly 30 nanoseconds. So we did this measurement. This is the full sequence. We prepare the nuclear ensemble, and then we're going to take a reference measurement, which informs us about the nuclear spin state before we do anything. Then we're going to drive selectively the nuclear magnon, and then we're going to sense the new nuclear state. So when you do this whole sequence, there's a few things you can extract. The first thing is simply the electron population here. That's the sideband spectrum that you have seen until now. And then we have the Ramsey signal from our reference and our sensing sequence. And this is the signal that you see here, where, you know, we see a negative signal if we're driving the negative sideband. So that's a first tick on our checklist. We actually have a signal which changes polarity depending on the detuning of our drive. The second thing is we actually see a cumulative shift. So in other words, we have a reference which depends on the drive detuning, which means that our preparation here is suboptimal. It doesn't fully erase the drive. But if we take the different signal between these two curves, you actually get and retrieve the single magnon shift, which is a measure of the hyperfine shift when you have changed the nuclear state by 1 unit. And this is what we see. And what's very exciting is that we not only see a shift in polarity, we actually start to see the emergence of additional structure in these peaks, which correspond to different nuclear spin species. So we see here by probing these magnons that our drive is actually selectively, is maybe strong of a word, but fairly selectively addressing arsenic or indium nuclear spins.
2 minutes left.
2 minutes left. So the next thing that I will touch upon is what can the electron tell us about the internal make of the nuclear state. So if you think about knowing something about a nuclear state or reconstructing a nuclear state, the traditional way of doing it is nuclear magnetic resonance. You do global control sequences and you can fully reconstruct the state using a classical radio frequency field. And the electron in our system is actually not too far off, except it's a quantum coil performing NMR via a single radio frequency photon. And, you know, until now, I've told you about collective enhancement, this root N enhancement if you have a many-body system. And you also have, I've told you a bit about the selection rules of our magnons if you're in the single nucleus picture. So I guess it won't be surprising to you at this point if I tell you that actually, if we look at these sideband processes from +2, +1, -1, -2, they actually relate to the single nuclear spin population. So the number of nuclei in the -3½ state, for instance, and thus by sort of probing what is the Rabi frequency of each sideband process, you can actually fully reconstruct the spin population of a 3½ nuclei. So this is great for the arsenic ensemble. For indium, I'll tell you at this point, we can only retrieve the polarization of this species, but we can't fully reconstruct the spin population. And yeah, I think I'll go very quickly on that one. It's not new physics, it's mainly data analysis. But the nice thing is that we have studied how you know, population imbalance builds up between, for instance, the 1/2 and the -1/2 spin projection for the arsenic nuclei, as we polarize the nuclear ensemble, giving rise to, you know, Overhauser shifts on the order of tens of gigahertz. And so we see that the population imbalance mainly builds up across the 3½ and -3½ spin projections. We see lots of interesting things, but they're quite preliminary. But yeah, this is all exciting. And
yeah, yeah. Exciting.
Thank you very much for your attention. Sorry, that was probably more than 2 minutes.
Yeah, it's perfect. Thanks a lot. So let's give a big applause to Claire.